This video looks at some solutions to deal with overfitting in machine learning. Just very briefly, overfitting is a situation where you create models on past data and the models perform quite well, but when eventually future data comes around, the models do not perform so well. So considering the relationship between overfitting and predictive performance, in particular using decision trees as an example, if you let a decision tree grow forever, that is, have as many branches, as many levels, as many leaves as possible, it will eventually go to 100% purity in each leaf, meaning that each leaf eventually predicts every point in the data set. You'll get 100% accuracy. Well, that's not really good because this overfits the data. And that means that you're not fitting the systematic patterns, but you're fitting the noise in the data. And so you're going to have low predictive accuracy for new data. Okay, so when you get past a certain point, the error rate for the validation data starts to increase. And we can see this with this little chart here, where on the y-axis, you have the error rate, where there's more errors in the predictions as you go up here. And on the x-axis, the number of splits. So you can think of that as depth of the tree, how much the tree branches out. And in general, for a decision tree to be accurate, it needs to branch out. It needs to have enough branches, some depth, and then it can more accurately represent the data set. But there are limits to that. So the blue line represents the relationship with the training data, and the green line is future unseen data. So let's look at the training data first. In general, as you increase the splits, which means the tree gets bigger and bigger, more and more detailed, the errors in prediction reduce. In the training data, they reduce and reduce, and if you let it grow big enough, there'll be zero error. It will predict everything in the data set perfectly. Okay. However, if you apply the same model with the same number of splits on future data, then at first, with like, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9 splits, the more detailed the tree is, the better it predicts the unseen data. The error rate reduces on the unseen data as well. But there comes a point, which is right about here, where, let's say at about 10 splits, when you go to 11 splits, 12 splits, so the tree gets bigger and bigger, that for the original data set that you trained on, it's still getting better, but for any new data, it actually starts getting worse. The predictions get worse and worse and worse, and the more you split, the worse it gets on future data at the same time that it was getting better on training data. And that's because in this part, you have overfitting. And the sweet spot is if you can find right about here, like maybe around 10 splits or so, where on the training data, things are getting better, but more critically, the future data, future unseen data, the error rate is reducing, but it's not getting any worse. And that's where you want to stop. And so a tree around 10 in this example, 10 splits will be just perfect. And so the goal of resolving overfitting is trying to find that sweet spot. So solutions to overfitting in general, ideally, we want to test models on new data. But the thing is that we don't know the actual value or class of response of new data because the new data, the future data, has not come around yet. So what we do is that we're going to, we have to, so there's different ways we can do that. We can try an automatic way, which is using pruning algorithms. And these are techniques that apply in some algorithms, such as decision trees, that kind of get a sense of when they're starting to cross the line. where it's training, but maybe it's looking good, but maybe it's looking too good. So there are different algorithms that try to detect that. Decision trees and RapidMiner offer the apply pruning option that does this, where it tries to get a sense that, okay, it's starting to become too good to be true, and it's probably good to stop now. That's the idea of pruning algorithms. And so that's just a configuration in the software. But there's a semi-automatic way, which is splitting the data set into partitions for split or cross-validation. And this is a standard approach that you pretty much have to do, even if you apply pruning algorithms, and we'll talk about that next. So the idea behind data validation is generally that you have the present data, and you would like to know what future data is going to be like, but we don't have future data. So this is all theoretical while we're modeling, but in real life, it bears out again and again. This happens. So we can't ignore it. How can we have future data to know how well our past data is performing? Well, we can pretend. And the basic way of pretending is that you split your data set. So you have maybe your data set from last year, maybe 1,000 records, and say, let's only use half of it to do the modeling, and let's pretend that the other half is what we get in the future. And if it performs well on the part that we train on, and it also performs well on the part that it doesn't see, then might do better. Because crucially, the part that you put aside, you don't tell the computer the answers. Part of it, you give the computer the answers, what is true and false, it can learn. The other part, it doesn't. So the simplest way, which actually works well to do this, is called split validation, which usually works with 2 partitions. It might also work with 3. And here you have a training set, which is usually at least 50% of the data. And here you give the model the answers, that if it sees the true or false answers that you're trying to give it, whether for classification, the categories, or for regression, you give it the numbers that you're trying to predict. And this works for both classification and regression. And you let it train and learn the patterns on the data that can give those true or false answers. And you hide the remaining set. And the remaining parts, the validation set, usually 25% to 50%. So if it's 25%, that means that the training set was 75% and validation set is 25%. Or you could do a 50-50 split. So with a validation set, you don't let the computer train on the true answers, but you take the model that was prepared on the training set, and then you now apply that model on the validation set and see how well did the computer do. And if the model does a good job in predicting on the data whose answers did not see, then that gives a good indication that it would do a good job in the future. And vice versa. If, on the contrary, if it does a poor job on the validation data set that it cannot see, it's an indication it's not going to do a good job in future data that you can't see either. Sometimes you might have a third pre-training set to optimize parameters, but that's somewhat advanced. So that's the basic idea of split validation. The state of the art, there's a more advanced form of validation that builds on the same ideas called cross-validation. And there, instead of splitting the data set into 2 or 3 parts, you split it up into many partitions, typically 10, which is called tenfold cross-validation. And you use 9 partitions at a time for training and 1 for testing. And then you repeat this 10 times, and each partition takes its turn being the test partition. And then you average the performance across all of them, and that gives you the eventual result. So that's a little bit complicated and beyond the scope of this video to explain in detail. But here's a couple of links. Here's a video tutorial that explains cross-validation very well. And it's also important to know that there are other variations that have pros and cons. And here's a good article that talks about many variations of cross-validation. But that's the general idea. One final to mention though is that even though you split the data sets, you do training sets, validation sets, maybe tenfold validation. Once you have your final model, uh, and you're trying to score the entire model, you'll do it on the entire data set at once at the end. So that's a brief video. This video has just very briefly talked about some basic solutions to the challenges of overfitting. And I know it's basic, but at least you get an overview of the issue.